Alright, so this is going to be our notes on free fall. We've been talking about motion and force so far, and if you remember, we talked about motion and we're talking about measuring where an object is in space, so how fast it moves from one spot to the other, and how fast its speed is changing. And then we looked at force and kind of started to understand that force is the thing that it's a push or pull on an object, but also, probably more importantly, it changes the speed of an object, or changes the velocity, or causes it to accelerate due to unbalanced forces. So the next thing for us to look at is free fall. So we're going to kind of do that today. And free fall has to do, if you have an object that is just falling, and the only force acting on it is gravity, F of g. So like if you were standing on a cliff, and you throw a ball, you tossed it, eventually it's going to get to the point where the force you applied is lost, and then it starts to fall. I'll put some arrows in here. Okay. Initially it has that force applied, F of A, but then eventually the only force acting on it is the force of gravity. Okay. Now, maybe I misspoke a little bit, because there are some forces against it, such as air resistance, and we'll go over that eventually here in just a few minutes. But really, there's no applied force and other than gravity. We call any object that's only under the force of gravity that as an object that's in free fall. Something really associated with free fall is this acceleration here. And we talked about in class 9.8 meters per second, and that is the acceleration due to gravity. So no matter what you are, if you're a car, if you're a person, if you're a hockey puck, it's a pretty big hockey puck though, and we take you and we put you in a plane, any of these things, and then we drop them. There's this interesting thing that the force of gravity due to the Earth, it then pulls on objects and causes them to accelerate at this speed, no matter what they are. So the acceleration in this car is 9.8 meters per second squared. The acceleration due to gravity of that puck, of that person, and so on, they are all 9.8 meters per second squared. Okay, and we're going to talk, or actually we're going to watch some videos that kind of talk about why that is. And inertia has something to do with it that makes these objects be the same. Inertia kind of plays into the factor, or the what's going on there. And there's two really important equations to know. One is velocity, and the other one's distance. So when we're talking about an object in free fall, if you want to figure out the velocity, we just need to take the gravity, which is this, and times it by the time, which is always going to be in seconds. If we want to know the distance, we take half times acceleration, which is 9.8, and then we do the time, then we square it. Okay. So let's do just a couple examples for you. So I'm going to erase here some things. Maybe I'm not. Let me do it this way. I'm going to plug in some examples. So if we have velocity, so this ball right here, let's do this one. So if we say gravity is always going to be the same, it's not going to change unless you go to a different planet. The moon will be different, different size planet, different size gravity, because gravity is based on large part on the size of the object. Okay, and then we would do the time. So if this ball was dropping after 3 seconds, where would it be? So we just plug that in. Then we would do the math. See if I can get to it here. Just use my calculator maybe. Let me grab it. And we would say 9.8 times 3 would give us 29.4. The unit for this, velocity, is going to be the same, meters per second. And it's always got to match up, because gravity is meters per second squared. So it's going to have to match up in the distance meters and in the time seconds. And if you have something that's not in meters, you have to change it so it is that. Otherwise, this equation will not work out. So that would be this ball's velocity. If we took the car and dropped it, it would be the same, and so on. Took the hockey puck, dropped it after 3 seconds, it would be the same. That's the only things that matter for that. Then we have distance. So if we did that, we go 1/2 times 9.8 times the time, 30 seconds, which we can square it. So let's do it. 0.5 times 9.8 times 9. And that will give us 44.1 meters. Okay? So then we can figure out, which is kind of cool because the free fall is just based on the acceleration due to gravity and how long. And we can then figure out the distance, 44.1 meters. So that's some examples of problems. That's how you do them. Make sure you put that in your notes. And I'm going to erase these and we'll just cover this last thing and we'll be done. Let me take these annotations off and move this down. Okay, so the last things we have to worry about are the other forces acting. And really the one force we're really worried about is air resistance. Okay? So air resistance does play a factor, and the other important factor is inertia. Okay. So you can say air resistance, and we'll put inertia down here as well. Inertia is just that tendency to resist a change in motion. So we'll just put resist change in motion. Like if you're riding in the car and you go around a turn, your body tends to keep going the same way you were going, and you kind of lean. Okay, that's inertia. It's just something that occurs to all objects in motion. Okay, so that means, so then you also want to remember with mass and inertia, as mass increases, so does the ability, or inertia itself. So the more mass an object has, the more inertia it has, the more resistance it has to a change in motion. So then if we get a giant car and we get a person and we're trying to drop them, and why do they fall at the same rate? Well, inertia factors into that because the car has a much greater mass and it tends to resist that change in motion as it falls a lot more than if we drop that ball. Okay, that's kind of how inertia plays into that. But air resistance as well. So we know if we took a ball like this, and we took a piece of paper, and we dropped it this flat side, just, so it was horizontal, the ball would fall much faster. You'd say, well, free fall doesn't work. But it actually does because air resistance can play a factor in it. So, so if the piece of paper is flat, it has more surface area, SA, and that causes more resistance, and that causes it to slow down at a greater amount. And that can also play into the car and other things as well. So that kind of explains some of that behavior. So air resistance does play a factor. The more aerodynamic something is, the less likely it is to be slowed down as much. And then the last thing is terminal velocity. And this is where things stop, their acceleration, their increase in velocity tends to stop. And it's still moving at a certain velocity, but due to air resistance and how hard you are in the air, eventually terminal velocity takes over and your acceleration or velocity will cease when you reach terminal velocity. And you've probably seen or heard of that before. That's due to friction in the air, because even though we can't see them, there's particles in the air and they tend to slow things down. Eventually, if you're high up enough in the air, it will cause you to reach terminal velocity. Okay, so that's kind of our notes on free fall. Make sure you add these to your notebook. And if you have any questions, let me know. You should also watch the other videos that will help you understand these topics as well. And that's it.